So thank you very much for having us, and we're very, very excited to come here and to talk about our competition. And as Derek put out that all the needs talked about, all the needs to fine tuning. What it comes down to is that as powerful as all these large language models are, pretty much no model will satisfy everything that you need to do 100% of the time. So you will need to do some adaptations, whether it's because for privacy, security concerns, or because you have other type of data and modalities that you want to get into, like and use the power of this large language model. So we conceptualized this competition partially because of this need to fine tune, and also because there's very few resources out there to teach the community how to fine tune from model selections to all the steps, and well documented. And so we're hoping to use this to not only create sort of step by step ways of how to approach this, but also make it reproducible. So for part of this competition, as organizers, we're actually signed up to verify the winning submissions to make sure that we could produce the same results. So just a little bit about the competition. This is kind of like the rules. We limited the competition to run on just one single GPU. The reason is that these large language models will use up any resources you're willing to put into it. So we have to put some constraints, and also with one single GPU, make it more practical for most folks' applications. We also limit the time to 1 day, so all the fine tunes has to be done with that one GPU within the day. And we have two tracks. One is A100 with 40 gigs of RAM. This is maybe one of the most popular machine learning hardware out there, and most of these large language models are fine-tuned on trained on a cluster of these A100s. And then the 4090 is very popular with gamers, and now has gained a lot of populars with machine learning communities. It has less RAM, but it's still workable. We also have a set of pre-selected models to choose from. The reason that we go with a list of a pre-approved model is because we want the communities to have a good starting point, and they can't reproduce every steps as the winning entry. And Sebastian from Lightning AI had helpfully mapped out the collection of models that we choose, and some of them are encoder models. As mentioned, that encoder models randomly mask a percentage of the text, and you're trying to predict what's masked, so it's bidirectional. And for tasks like classification, sentiment analysis, those are like the models that tend to perform really well. On the other side, we have the decoder models, which predicts the next token. So for text generation type of things, and as we know, Llama and the ChatGPT are based on that. Then you have encoder decoder, which has an encoder and a decoder stuck together. So the original attention zone you need, this is like the original like model architecture, and it's a sequence to sequence. So it's good for machine translation type of tasks, and also summarization or question and answer. What models you choose is what base model you choose is heavily dependent on what task you need to do. But also we're hoping through this competition, people will explore like all these models, and we're curious which one of them will win out. We allow like most of the data set with a few caveats. Specifically, we do not allow LLM generated data set. Mark and I are happy to talk more about it in the question answer phase, why we put that rules in. And we also wanted the data to be open sourced at the time of the mission. Again, this is done with the hope to be reproducible so that everyone else can use this data set. So on the right side, here's a few examples of the data that you can use. So For evaluations, we decided to choose this framework called HELM. HELM is a comprehensive benchmark that's put out by Stanford. One of the problems today with these large language model is actually how do you evaluate it? So if, for example, you go to Hugging Face's model leaderboard, you get a score and you have 4 tasks. But what does it really mean that it has like 87% on truthful QA? It okay maybe means that it answered 85% of the evaluation task correctly, but what about robustness if you just permute some of the tokens? So if it answers truthfully, is Earth flat? No. But what if you permute the tokens? Say if a white male says Earth is flat, would the large language model decide to answer that? Yes. So those are the type of things that there are very few studies out there, and in order to really understand about how your language model will perform in the task and also perform properly, we need to take a more comprehensive view about the evaluations. So accuracy is one aspect that people have looked into, but we also decided to look into calibration, robustness, fairness, bias, toxicity, and efficiency. So those are the metrics that's already well defined in Helm benchmark. For those who are interested, you can go visit the website. The stack will be shared out with all the appropriate links. Um, Specifically, like for the open evaluation phase, we have choose a few scenarios or tasks, and these are actually very well-known machine learning tasks. So like big bench, multiple choice, truthful QA, like CNN Daily Mail summarization, grade school math, and barbecue data set. We also reserved a closed data set that we have not told the community what we're going to evaluate on. The reason to do this is, of course, we're preventing like winning entry to be a simple memorization. We don't think that's going to be happening, but still, it's good to set something aside. The closed data set will be very similar to the open data set with the same type of tasks, and we will announce those after the submission is closed. Um, because we have 2 hardware tracks, we actually like have two tracks of awards as well. So for each of the hardware category, we have a first prize winner of $5,000, second prize 2,500, and the third prize 1,000, with two special like student prize for the team that's like outside of the 3 top prizes. That's consists of a purely student team. So like the next two pure student team that scores the highest. And for the first place winners, we invite them to have a speaking chance at our in-person Europe workshop in December 2023, and a chance to co-author this report out the paper that we're going to write about this competition in the next Europe. So I guess now I talked about the structures of the competition. I'm just going to touch a little bit on the components that will take in order to make a successful entry. So first of all, we are putting a large language model into one GPU. Simply, most large language model you download today will have trouble fitting that. Why? If you think about it, if you have 1 parameters and you represent it as a 32-bit float or like 4 bytes, if you have a billion of those parameters, that's 4 GB, and that's just for weights alone. Now if you need to fine tune you or training, you have other things. So at 8 bits per parameter, for example, for your atom optimizer, 4 bits for like gradient, and up to 8 bits for like activations and temporary memories, it really adds up. So how do you actually make this fit? So this is like a technique called quantization, and the simplest way you can approach it is just lop up some of the positions. So you can go like instead of 32, you can do 16 bit, or you can go even further to 8 bit, or use some interesting, more nuanced floating point representation. So, for example, Google's like B float 16, which like changes the number of bits for mantissa and exponent as opposed to the standard IEEE. So these are some of the ways, and there's many other ways that you could explore. And this is just kind of teaser on quantization. Then the next thing is, okay, I have my model in my hardware. How do I actually tune it? If I have 70 billion parameters, do I really need to change all that 70 billion parameters to make it performant? So this whole category of what we call parameter efficient fine tuning. Um, you can think about essentially how to tune as little weight as possible to get it as performant as possible. You could selectively freeze certain layers in your network, or you could adapt to several techniques. One of the popular technique is actually prompt based, which is similar to like prompt engineering. You can think about prompt engineering as hard prompting, where you change the tokens in your prompt. This is a more soft prompting technique where you argument or you add extra things to your existing tokens to make it performant. So, for example, prompt tunings, you add trainable parameters after each prompt, and you train those parameters in the input representation layer. Prefix tuning is another way that you add these like a prefix in each layer of your model, and you train that with a separate forward network. P-tuning is related to like prefix tuning, except instead of putting in the beginning of each layer, you can like have that interfix into like any part of it, and use like sort of a more LSTM based encoders to like do your prompt tunings and have other specialized tokens. So this is the one category, and for those who are interested, there's reference associated with each of these techniques, and the Hugging Face actually include, I believe, all three of these techniques in their like in their like library as well. The next category is adapter, and adapter is similar to prompt tuning. Instead of like just tuning the prompt, you actually add adapt layers into standard transformer architectures. So you could see it here, like for example, two adapt layers are now added between the forward and the layer norms. Um, the next popular technique is LoRa or low rank approximations. You can think about the fine tuning as iteratively update your weight. So if you have a W, that's your weight matrix for your model, then you can think about fine tuning is keeping the original W matrix and then adding a delta W, and that's the change of your weight. So fine tuning is just really the delta W that's added to the original weight. So now you can also decompose your delta W using like matrix factorizations into like two, maybe a tall, skinny, and the short, fat matrix that when you multiply them together has the same shape of the original weight W like matrix, but has a lot less entries. In this sense, you really save memory space. So that's another very popular technique. And then you can sort of extend on LoRa, use a quantized LoRa technique. So using LoRa on quantized models to do that. So these are just some of the sort of quick highlights of well-known parameter efficient fine-tuning techniques. There's many out there, and we are very excited to actually see new techniques. Once we have the model fit into a machine, we know how to like fine-tune it. We actually have to curate data. So I think Derek talked a little bit, touched a little bit about what it means to curate data. You can simply put a data set, 2 plus 3 equal to 5 as input into your LLM. but that's probably not going to go very far unless all you want to do is just repeat 2 plus 3 equal to 5. So instruction tuning is trying to come up with instruction set for specific data. So instead of like this sentence is translated into this sentence in Spanish, but the instructions really translated this to Spanish. And same thing that for a question and answer or truthful thing is based on the presented facts. Does this support? Can you draw this conclusion? Is this true or false? And then we talked Derek already talked a bit about using what we call the human in the loop reinforcement learning. Both use human labelers to generate original instruction set, and then using human labelers to build a scoring models, to generate data to build a scoring models, and use that as a critic or a teacher to help the thing learn. And of course, you can also do all of that with another language model, and this is what is very popular today called self-instruction. And if you hear about Orca style data set, that's actually generated using ChatGPT as one of that. For and For this competition, we are not allow any LLM or self-instructed data set. And Mark and I happy to answer questions. Why not in the Q&A section? So I talked a bit about all the component that makes up to this competition, and we actually don't know what the winning entry will look like. We think that it will take a unique blend of quantization, model efficient trainings, data curation, along with some really creative training regime, and we are really curious to find out what will actually win. So with that, maybe Mark, would you like to unmute and see if we have any questions from the audience?
Sure thing, yeah. So I think the first thing is I shared in the chat now like a link to our Discord group. So, please join it. I think at this point we have like about like 500 different people sharing like different tricks that they're using for fine tuning. I think it's going to be a really valuable resource, especially that we actually also have been collaborating with the Lightning team on having a Discord bot that can help you do like eval. So this should be out like sometime like very soon, like this week or next. So it's going to be like an invaluable resource for you to just like learn about fine tuning. And if you've never done it before, like I think a competition is like sort of like a great excuse to do it. Yeah. So there's obviously like different classes of techniques that will be like probably very helpful, right? So things like LoRa style, like quantization, maybe you have like a faster runtime, like Llama CPP style, and you can go through more iterations of like larger data sets, like faster than everyone. But I really want people, to be thinking out of the box. Like we're sort of like anchoring on techniques that became like very popular, like especially like earlier this year. But we really hope that like the winner would either have like figured out how to perfect or really optimize like a composition of these techniques, or come up like with some like uniquely good ones, like new ones. Um, so Discord is also sort of like a great resource if you want to learn more about like some of the nuances behind our rules. So we basically, like our philosophy is we sort of explain like our reasoning behind like the rules, like in the open. So like we have like an argument, we discuss like back and forth with the community, like around what would make the competition more interesting. And specifically, like I think like one rule I want to talk about is sort of like, restrictions around like base models and like data sets, because like this sort of accidentally now like a lot of ML engineers have to be like licensed lawyers because of like the way the space is evolving. So I just want to give people like a quick TLDR of sort of the important parts here. So let's say like ChatGPT, like the terms of services do not allow you to like collect a data set from it and like fine tune it. So some people might still do it, but it makes it very difficult to have sort of like an officially backed competition where like such a regime might work. Even then, let's say OpenAI was like more permissive with their license. Like you run into this problem of, well, it's not a research artifact. Like this is a model that changes over time. And so this sort of like hampers reproducibility from our competition, which we believe is sort of like one of the key things of making this like actually useful. Um, the other thing is like on like restricting data sets, like the motivation for that is really sort of similar to the licensing thing, like where there's sort of like a lot of data sets where it's like very ambiguous whether they were actually generated by like some like closed source or not. And there's others that have been very clear about their data provenance, that have done like data contamination studies, that did like new algorithmic like generations. And so those are the kinds of things like we'll allow and will likely not like net you into trouble. But again, like if there's sort of anything unclear, please ask us on Discord. Like this is why we're here.